So we're gonna start with the position function in the form of s, or s as a function of t. Okay, s as a function of t. The basic form of the slope that you are familiar with based on y as the function of x, and the order pair is in the form of x first and y second, or the first coordinate as a x, second coordinate as a y, or x as the independent variable and y is dependent variable. Okay, now if we look at the certain application like the position function s of t, the coordinate will be in the form of t comma s, because you have the input as a t, so t is the independent variable and s as the dependent variable. If I form the order pair, I have t comma s. Now instead of using the order pair x1 y1, I'm using different notation. Like if this is my t0 and this point is my t1, so the coordinate over here is going to be in the form of t comma 0 s comma 0. Okay, just map it out like from xy version to the st version, and this is my t1 comma s1. Okay, s as a position and t as a time, so I'm gonna find another version of the slope. It's called the slope of the secant line, or use just m subscript sec, using the two order pairs, the st version. Okay, it will be in the form of s1 minus s0 divided by t1 minus t0, or s at t1 minus s at t0, all divided by t1 minus t0. You guys follow okay with this concept?
Yeah.
Term by term.
Yeah.
Very good. So the red line here is the line, it's called secant line. So I'm calling here, this is a secant line. Secant line, or the line that's cutting across, passing two order pairs. By this application, as you see, the top portion is called the change in position. The bottom is the change in time. Okay, change in position per change in time. It is called the average velocity. So I call m of the secant line is the average velocity. Okay, now if I move, so I'm gonna stop using the annotate. So I'm gonna get rid of this one. So if we move the point here closer and closer and closer to the other point, you see the simulation here. Further away, I have the secant line is very obvious. As I move the coordinate here closer and closer to the original or the beginning point here, almost the same. And you see the line, the red line and the dotted line, almost the same one, right? Almost the same one. The dotted line here is called tangent line. So as I move T1 approaches to T0, the slope of the secant line approaching the slope of the tangent line, because the line almost on top of each other. Does it make sense to you guys? You guys okay with this? So it's coming closer and closer. So that means as far as I get it very close to each other, I almost get exactly the same line. Okay. So the term that I use the way that I let me put in the form here. So as t approaches t0, the slope of the secant line approaching the slope of the tangent line. And what I mentioned earlier, the slope of the secant line, which is the change in position over change in time, or another way we call it the average velocity. So what do we call for the secant, for the slope of the tangent line? We call it instantaneous velocity. Okay, velocity. So that means as t1 approaches t0, or the gap, which is the change in time, or t1 minus t0, if it approaches 0, or the gap is very, very small, the two coordinates almost the same. They are not the same, but so close. So that means the difference in time is so small. So we can say that the average velocity approaches instantaneous velocity. In the formula form, that means the slope of the secant approaches the slope of the tangent line.